Hello students, today we are going to be going over endocrine system objectives number 2, 7, 8, 9, and 10. 2 is your overview of the endocrine system, whereas the rest are about your pituitary gland. So let's get going. So we're beginning where we left off with our endocrine system to go over y'all's overview of your endocrine system. Just a reminder, all of these glands that we are discussing right now are indeed endocrine glands. They are not exocrine, they are endocrine. Right? The glands that you guys will need to know, first and foremost, the hypothalamus here is what translates nervous system impulses and information into endocrine information. So the hypothalamus is the translator between your two systems. Other than that, we have in front of the hypothalamus here, dangling down, is your pituitary gland. That will be the rest of the focus of today's lesson. Behind the hypothalamus, we have the pineal gland. Your pineal gland controls your circadian rhythm when you're awake and when you're asleep. Your pituitary does a great deal. That will be the rest of this video. If we travel on down, circling around your windpipe is your thyroid gland, which controls your metabolism. Your parathyroid glands are smaller glands that are located on the back of your thyroid. Keep going down the body, and you will find behind your breastbone or your sternum your thymus. We will talk more about your thymus in your immune system, really, because your thymus has more to do with making your white blood cells and immune system strong. Traveling on down the body, on top of the kidneys, like little bitty triangle hats, would be your adrenal glands. You have 2 adrenal glands, one on top of each of your kidneys. Curling around the bottom part of your stomach, you have the pancreas, which is responsible for your blood sugar levels and sugar use throughout your body. And then the last 2 on our list that we will be discussing are sex-specific. Females have ovaries, and the ovaries' job is both to help create estrogen as well as create eggs for our reproductive cycles. And the men, or males, within our group have testes, which produce testosterone and are responsible for sperm production. For the most part, as far as our endocrine system is concerned, we're only going to gloss over these 2 and let you know that yes, indeed, they make hormones and they are there, but you don't have to know the true functions of them or their specifics until we get to the reproductive system, when I have to explain to you how the ovary grows and matures eggs and how the testes grow and produce sperm. That is for the last unit of this semester, so we won't be focusing there. You just need to know that ovaries are the gland that females have that make estrogen, and testes are the gland that males have to make testosterone. Right? And as a happy little reminder, you have other organs in your body that do indeed make hormones. This is not the end list. However, most of these other systems that create hormones, like your small intestines, your stomach, your heart, kidneys, those produce hormones that only affect really that one system in the body instead of going full system-wide. So we won't be discussing those hormones specifically in this chapter because we're talking about the big ones that do go body-wide, that will affect everything. But we will discuss those individual hormones when we get there. So when we talk about the hormones that your heart can create, that will be when we talk about your cardiovascular system and that kind of thing. So don't freak out too much over these. in this slide. Just focus on what y'all gotta know now. So objective number 7 and 8. Objective 7 is describe the regulation of hormone release. And objective 8 is describe how the structure of the hypothalamus and pituitary glands relate to their function and functional relationships. So discussing this, right, you have this lovely image of the brain right here. You will see this picture again when we talk about the pineal gland. But we know that this is your brain. You guys went over it in your nervous system. We know that this is your hypothalamus region. And we know that the pituitary gland dangles off of your hypothalamus. It does look like a pair of testicles, but they are sideways facing instead of front facing, meaning you have a frontal lobe of your pituitary gland and a back lobe of your pituitary gland. Because this is anatomy and physiology, we're going to use your fancy proper terms you learned in A&P 1 for that. So if something is forward facing or toward the front of the body, it is anterior. And if something is backwards facing or toward the rear of the body, it is posterior. So you have an anterior pituitary that you need to know about and a posterior pituitary that you need to know about. Okay. So your pituitary gland here dangles off of your hypothalamus and sits in this little bone here called your sphenoid, if you remember from the skeletal system way back in A&P 1. Your sphenoid bone looked like a butterfly in your brain that held up your brain, and it had a little saddle area to it. And that saddle area is where your pituitary gland happily sits down and just resides for your entire life in that sella turcica. Your pituitary gland, based upon if we are talking about posterior or anterior lobes, have different jobs and have very different jobs. And this is why we start talking about the structure of the hypothalamus and the pituitary glands. So your posterior pituitary has a much stronger relationship to the hypothalamus than your anterior pituitary does, although your anterior pituitary does talk to it a lot. Your fancy term for the pituitary gland is called the hypophysis. Occasionally they like to throw that word out there on the final exam just to confuse people, which is why it's also listed on y'all's lab list. But the hypophysis is your fancy terminology for pituitary gland. 9 times out of 10 it's going to be referred to as the pituitary. But your fancy terms for your pituitary lobes, just so you know, the posterior pituitary can also be called the neurohypophysis, and the anterior pituitary can also be called the adenohypophysis. When we start talking about them specifically, that will become apparent why. But when we start looking at their structure and function, because your hypothalamus is the translator and switchboard or operator between your nervous system and your endocrine system, it has a great deal of blood vessels, it's very vascular, and it has a number of nerves because it's neural. So we have a lot of neural input, and we have a decent bit of vascular input, because remember, hormones travel body-wide through your bloodstream, and they are vascular, whereas nerve impulses are electrical and through your nervous system, or neurons. So your hypothalamus is the data center that takes in information from your bloodstream, chemical information, how much sugar do we have, how much this do we have, how much that do we have, and your nervous impulse information, and just translates it between who needs to know what from those systems. Your posterior pituitary is very much the same. It has very much the same tissue structure. It's also very vascular and neuro. So your posterior pituitary talks a great deal to your hypothalamus, and to some extent acts as though it's an extension of it. Your anterior pituitary still takes orders from the hypothalamus, but it does its own thing a little bit more and produces more hormones therein, right? The majority of the hormones within your body work on what is called a negative feedback system. So your hypothalamus is constantly reading data from your body, and then when something goes too much or it needs to stop, it tells your pituitary glands, hey, we need this to stop or we need this reaction. And then your pituitary, through hormones, sends messages to the other systems in your body for them to do their job and correct whatever the hypothalamus has detected. And then when the hypothalamus thinks everything is fine, those hormones are told, hey, you can chill out and stop now. And it works in a nice cycle like that, which is what negative feedback is. We discussed that last time. Right? This leaves us with our endocrine objectives 10 and endocrine objectives 9. I know this is slightly confusing, but we are going to skip to endocrine objective 10 first, so we can discuss the posterior pituitary before we talk about your anterior pituitary. So your posterior pituitary gland has tissue that is very much like the hypothalamus. And just like the hypothalamus, two hormones are associated with your posterior pituitary. You have oxytocin and ADH, or antidiuretic hormone. You guys have already seen both ends of this and both bits of this information that may be conflicting. If you are reading your lab notebook to keep up with things, you will see that the lab notebook explicitly tells you that the hypothalamus makes these hormones and the posterior pituitary merely stores the oxytocin and antidiuretic hormone until ready for release. On the flip side of things, our OpenStax textbook and this PowerPoint that came with the OpenStax textbook tells you that your posterior pituitary synthesizes oxytocin and antidiuretic hormone and then stores it. So your textbook and your PowerPoint tells you that your posterior pituitary does both jobs. Your lab manual tells you that the posterior pituitary only stores it. Either way, I'm not here to nitpick which does which. I want you guys to associate oxytocin and antidiuretic hormone with your posterior pituitary, because in all likelihood, it probably synthesizes some of those and it stores what both it makes and the hypothalamus makes. But because your posterior pituitary is very, very close to your hypothalamus, it also has a great deal of nervous tissue to it, more than your anterior pituitary does, and it has a lot of vascular tissue. So your posterior pituitary is going to function almost like a mini extension of the hypothalamus and also store the two hormones that the hypothalamus itself does make. Right? The only hormone that you guys truly have to worry about that is not a negative feedback mechanism would be oxytocin. That is a positive feedback mechanism. Oxytocin stimulates uterine contractions for childbirth as well as making you feel love and happiness. When your baby gets big enough and has flipped over, the head is pushing down on the cervix when baby's ready to be born, and your body can feel that this muscle balloon of your uterus is essentially stretched out enough. When it is stretched enough and the cervix toward the end of your gestation begins sending impulses to your hypothalamus stating, hey, your other hormones are making me thin out, we can't handle much more of this, your hypothalamus and your posterior pituitary are going to begin to release oxytocin in bursts. This is not an on-off switch. This is not a trigger. It's not like your body arbitrarily decides, oh, birth, baby now, and you give birth in 30 minutes. It takes time for this hormone to build up, and it can take longer the first time you give birth as opposed to the third time you have a child. But generally speaking, what will happen is that those muscular impulses that have sent signals up to your hypothalamus say, hey, we're ready to give birth, kid needs to get out. And your pituitary will release a little bit of oxytocin, which causes those calcium channels. If you remember from your muscular system how muscles contract via calcium channels triggering them. So oxytocin sends messengers that mobilize all those calcium channels, and the uterus begins to contract like any other muscle does with calcium. The cervix and the uterus still send signals up to the hypothalamus saying, hey, baby's still here. The hypothalamus gets that, says, hey, posterior pituitary, do your thing, and you release more oxytocin. And this trigger keeps happening until the baby and the placenta has left your body. So you keep making more and more and more oxytocin until you get to the point where the baby has been pushed out and the placenta has also come out. At that point, because this hormone was released and so it could continue to amp up this effect, then it stops. This is a positive feedback mechanism. And these are the only positive feedback mechanisms we're going to discuss during this chapter. Breastfeeding will also produce prolactin, which is a positive feedback mechanism. So the act of a baby suckling stimulates your brain to send signals down to your breast tissue to make more lactate, like more milk. And it also releases oxytocin, so that makes you bond and love your child even more. And that's that lovely hormone cycle. But these are the only real positive feedback mechanisms we're going to discuss. Everything else pretty much is a negative feedback mechanism. I know I just told you that the majority of this was negative. We just got the one positive mechanism out of the way in discussing this. But now we're going to talk about antidiuretic hormone. So in our lovely world of lavish resources and tap water and other such things, remember, tap water hasn't existed the entire time the human species has. That didn't happen like a few hundred years ago. You had to find a water source and dig a well, right? So our bodies naturally have a way to hold on to water when we feel like we are becoming dehydrated, and that is antidiuretic hormone. So antidiuretic hormone basically, here we go. Antidiuretic hormone here, I'm sorry, I skipped a slide before, is going to essentially, when your body feels like your blood pressure has dropped or that you are becoming dehydrated, you don't have enough liquid in you, your your hypothalamus detects that because of its vascular and neuro capabilities. And it's going to be getting both vascular signals of low blood pressure and neurological signals from various arteries within your body saying, hey, pressure's going down, and that kind of thing. Those are called baroreceptors. And your hypothalamus is then going to tell the posterior pituitary, hey, release the ADH, we need to hold on to some water. An antidiuretic hormone has two main targets, or many main targets, but it does two things. It goes to the major blood vessels in your body and causes them to constrict or tighten up. That will increase your blood pressure and make sure that your blood pressure stays high enough to feed the rest of your body, or to keep feeding your body. Much like a hose, you can't really... If you're thinking about, not necessarily a hose, I phrased that wrong, my apologies. If you're thinking of a watermill, right? You have to have that giant wheel on the side of the watermill, and the river flows strong enough to turn that wheel to make the mill work. If your blood pressure gets too low, the same kind of concept happens in your body. If blood pressure is too low, things can't function and the blood doesn't pump well. So ADH will actually cause your blood vessels to constrict or get smaller and tighten up in an effort to attempt to increase your blood pressure. And antidiuretic hormone, because it's anti-diuretics, it wants you to keep water, sends a signal to your kidneys and tells your kidneys, hey, dial it back a bit. You don't need to filter as much right now. We need to hold on to water. And without getting into too much detail of your kidneys, because that is your urinary system unit a few units from now, your kidneys then say, all right, we'll only filter out the worst waste byproduct. We will tighten up and make sure that we only get out what needs to get out. Otherwise, we'll hold on to extra water. And between the two of those things, the outcome is generally, because you're holding on to more water, your blood volume increases a little bit. And because your blood vessels have constricted, your blood pressure goes back up to normal levels. Right? So this is what antidiuretic hormone does. It makes your blood pressure go up, and it causes your blood volume to go up. We are going to talk about a disability with this. And this is one of 4 types of diabetes that you guys need to know about for this unit. The other 3 types of diabetes, I'm sure you guys have already mentally said, but isn't this the pancreas? The other 3 types of diabetes have to do with your pancreas. This is the only type of diabetes that does have to do with your posterior pituitary. And this is called diabetes insipidus. If you translate this directly from Latin, diabetes means overflow, and insipidus means tasteless. The reason why diabetes is called diabetes is because before we knew about insulin and before we knew about blood sugar levels, the main symptom of diabetes people could look at and detect was this individual is urinating a lot and this individual is drinking a lot of water. So the disease was named after those symptoms, essentially, right? Which is our key symptoms of all types of diabetes. So diabetes insipidus results from ADH deficiency. So your body essentially, for whatever reason, stops telling itself, hey, we need to hold on to water. And you just keep filtering everything out, and your kidneys keep filtering all the waste and all the water out. So because of diabetes insipidus, you get super thirsty super fast. And you keep having to drink and drink and drink, but you're also urinating a ton because of that. Diabetes insipidus in modern times, it can be caused by pituitary tumor. It can also be caused by craniotomies, which is when you do surgery on the brain. A lobotomy is within that realm. We don't do lobotomies anymore. We know better now. This is not the 1950s. But your general most common modern cause of this would be head injuries. Because if you sustain a bad head injury and the head injury damages your hypothalamus or your posterior pituitary, it may mess up your body's production of ADH. And if that happens, it means you may be diagnosed with diabetes insipidus, or you may be diagnosed with SIADH, or Syndrome of Inappropriate ADH Secretion. Don't get hung up on the word inappropriate. It just means for whatever reason you aren't producing the correct amount of whatever. So inappropriate, when we say inappropriate with hormones, it could be too little or too many. But diabetes insipidus, generally speaking, it's not going to be that big of an issue for people who are paying attention to it and up and awake and conscious. It produces a much more life-threatening problem for those that are unconscious or in a coma. So this is why the hospital will monitor people with head trauma, or one reason why hospitals will monitor people with head traumas more carefully and make sure they are intaking a correct amount of liquid and urinating a correct amount of liquid as well. And with that, we're going to swap to objective number 9, which is list and describe the actions or hormones within the anterior pituitary. So your anterior pituitary here is much more vascular than nervous, although it still talks closely with your hypothalamus. Your anterior pituitary is more like a manager, right? It produces 6 hormones that it secretes and releases into your body. Okay? The 6 hormones can be divided into 2 groups of them. They are either going to be tropic hormones or non-tropic hormones. Tropic hormones are hormones that regulate other endocrine system glands. So your manager hormones that tell other endocrine glands to do to make other hormones to do jobs are your tropic hormones. And your 4 tropic hormones are follicle stimulating hormone, or FSH. That stimulates your body to produce follicles, and that hormone is generally sent from the anterior pituitary down to either the testes or the ovaries, because this is the hormone here that tells your testes and ovaries, hey, it's time to grow an egg so you can release it and reproduce, or you have low sperm count, you need to produce more sperm. So in order to grow sperm or egg, follicle stimulating hormone is sent from your anterior pituitary to your ovaries and testes, and then they produce the egg and sperm. Luteinizing hormone, which is the opposite of follicle stimulating hormone, is also produced by your anterior pituitary, and it tells, once again, your testes or your ovaries, hey, chill out, you've produced enough. So when we get into the reproductive cycle, ladies, you will know down to the day what this cycle is supposed to be, because you have an ovarian cycle and a menstrual cycle, and your ovarian cycle is between these 2 hormones, and when you're building up an egg to release, and then when you need to chill out and just relax and heal after you have released it, which is what luteinizing hormone is. We will get into that when we talk about our reproductive system. But luteinizing hormone is the hormone that your pituitary will send to these other glands, telling them, hey, you've done enough, you've made enough, you don't have to stimulate any more follicles for right now. For gentlemen and men, this is not a monthly cycle, this is your nervous system checks, do you have enough sperm that are in storage within your epididymis and system ready to go? All right, we have enough, keep sending the luteinizing hormone. Oh, hey, look, we just had happy fun times. Send up the signal, make more follicle stimulating hormone. 12 hours later, you're fine again, and you get more luteinizing hormone. This is more of a fill up, we're full kind of hormone system that fluctuates throughout the day, because sperm production is, quite frankly, far faster than your ovarian production with eggs are. The other 2 tropic hormones, you have this lovely hormone here called adrenocorticotropic hormone. Right? Your adrenocorticotropic hormone, or ACTH, is the hormone that your pituitary gland makes to send to your adrenal glands here, that tell your adrenal glands to do their job and start making their hormones. You're going to have an entire video dedicated to your adrenal glands and the adrenal cortex here. I'm not going to get too much into that now, because your adrenal gland, quite frankly, will be the biggest headache in this unit. And the 4th tropic hormone is thyroid stimulating hormone, which your anterior pituitary makes after it has detected your energy needs and hormone levels, and it sends that signal, thyroid stimulating hormone, to your thyroid to tell your thyroid to do its job and manage your metabolism. So, hey, metabolism is weird. Hey, go handle that. This is your job. Go do that. That's what thyroid stimulating hormone is. Your brain, your hypothalamus detects stuff, tells your pituitary to handle it, and then your pituitary says, thyroid, you're supposed to handle it. That is what thyroid stimulating hormone is. It stimulates your thyroid to do its job. The other 2 hormones are non-tropic hormones, so they're hormones that just do their own job that your anterior pituitary makes, are prolactin, which is the hormone that is pro-lactation. It makes you make milk. So once you have enough stimulus here with a child trying to breastfeed from you, it will send a signal up to your anterior pituitary, and your anterior pituitary will tell you, hey, start making breast milk. And that's the hormone that does that, is prolactin. And growth hormone here is sent system-wide to your entire body from your anterior pituitary, and it tells your soft tissue and your bone growth plates and whatnot, hey, it's time for us to grow up big and strong, we need to grow, and you grow. You have a little bit of growth hormone in you your entire life, because that is what enables our cells to grow and repair as we get injured and things like that. But children have a lot more growth hormone than we do, because they actually need to still grow. They not only need to repair their cuts and bruises and scrapes from skinning their knees, but they also need to grow up big and strong. So children have more growth hormone than adults. Right? And that is all of the stuff that your anterior pituitary keeps track of. There are some case studies or some deficiencies, and I know you guys need to write this in to your note-taking guides off to the side. But there are some disorders with your pituitary that you should know about as well. And this is the last thing we're going to go over in your video. So, gigantism is a disease caused by hypersecretion of growth hormone in children. So, hyper means over or too much. So if you see hypersecretion, it means your body, for whatever reason, is making far too much of something. So if you are a child and your body your body is making way too much growth hormone or hypersecretion of growth hormone, it will cause you to grow way too much. That disorder is called gigantism. That's going to affect your epiphyseal plates. Those are your growth plates in your bones, remember. And you're going to be a much taller individual. You're going to be a giant amongst mankind, right? Gigantism causes individuals to keep growing, and they get super big. If you're looking for an animal in the animal kingdom that we associate with gigantism as well, that would be the liger. If you've ever watched Tiger King and that kind of show. So a quirk with ligers is they are not natural animals, because tigers and lions are on different continents naturally. And when you mate a male lion and a female tiger, they actually do not have these other hormones that I've skipped over that y'all don't really need to know, that inhibit growth hormone or tell the body, hey, we're fully grown, we need to stop growing anymore. Just genetically. And ligers have gigantism, and they never stop growing throughout their lifetime, which is why most of them end up dying from heart conditions and problems, because they inevitably get too large for their heart to keep up with, and they die of a heart attack because their heart cannot handle the size of their own body, which consequently is a medical issue that we, humans with gigantism, may happen to encounter if it's not contained or helped with modern medicine. If for some reason you became a regular normal adult and then your body suddenly started creating way too much growth hormone again, and for hypersecretion in adults, you end up with a different disorder. That means that your body had already decided to stop growing. You were already a full-grown adult, and then all of a sudden something happened, head injury, tumor, something, that made you start producing growth hormone like a child again. And that disorder is called acromegaly. Acromegaly means your body is trying to start growing again, but because your epiphyseal plates have already sealed, it really can only affect places like your hands, your feet, your face. So people with acromegaly may end up with like their hands widening and getting bigger as an adult, and their face also widening and getting larger, as well as their feet, but the rest of their body, like their torso, stays the same size. This generally means something is going wrong with the pituitary, or something has happened that's bad and needs to be treated. On the flip side of things, if your pituitary gland does not make enough growth hormone, that is hyposecretion. And that gives you a form of dwarfism called pituitary dwarfism. It slows down bone growth in children and results in far shorter and diminished height, because your body is not making the growth hormone to grow, even though you're trying to and you're going to end up being an adult. So this is a form of dwarfism, and this individual is going to end up being short if this hyposecretion of growth hormone is not dealt with. And I'm going to tell you, or leave you, with a case study about this. So there was a gentleman in history named Adam Rainier, right? He was born in 1899 and ended up being a dwarf. He was Austrian. He was born to normal-sized parents. But he wanted to do his patriotic duty when World War I rolled around. So when he turned 18 in 1917, he tried to enlist in the Austrian army to fight in World War I. But at the time and they measured him, he was literally 3 feet 10 inches. So 2 inches shy of being 4 feet tall. And the army, of course, rejected him because he was too small and weak, quote-unquote, to be a member of their army. Done deal. He was rejected from the military at age 18. However, a few years later, he started to grow, and that was quite weird, right? Because you normally stop growing when you're in your early 20s, and he started growing in his late 20s. And by 1931, he had actually been diagnosed with a tumor on his pituitary gland. He was given surgery to fix this, to remove the tumor, which I can't tell you how that's a risky surgery to do nowadays in modern medicine in 2020. This man had brain surgery to remove a pituitary tumor in 1931. It is a miracle he lived through that 90 years ago. But he underwent his surgery and he had the tumor removed in 1931. However, the removal of the tumor caused his pituitary to completely screw up, and he started making all the growth hormone that he had never made before in his life. So he then went from being a dwarf of 3 foot 10 inches to suddenly having an odd combination of acromegaly and gigantism. And he grew. And he grew. And he did not stop growing. If you're looking at this height difference here between a regular average-sized man and himself, once again, he looks like a very large person in his top hat here. This is a regular human next to him. Right? Because his body could not sustain or handle that growth and how quickly he grew, his spine became slightly crooked. He ended up bedridden before in his late 30s, he was bedridden. And by the time he died at 51 years old in 1950, he was 7 feet 10 inches tall. So this man, Adam Rainier, who was born in 1899, is the only man in recorded history who was both a dwarf and a giant in his lifetime. He died a giant at 7 feet 10 inches tall, but when he was 21 and 18 and attempted to enlist in the military, he was less than 4 feet tall at 3 feet 10. And that today is where I will leave you, my lovely ladies and gentlemen. Keep an eye out for the next video. Your next video is more than likely going to be over your thyroid and parathyroid glands. Have a wonderful afternoon.